All right, friends. So hopefully this looks all right. We are going to get started on this project too. I am in charge of the ANSYS part on my team. My name is Morgan Cosgrove, and hopefully you can learn something from this. I have my handy dandy Red Bull. And as you can see here, I already did a trial for this. So we're going to make a new one. All right. Now we're going to go to our geometry. We're going to go into Design Modeler. Exactly. Okay, so for this project, we are going to be doing a 2D flow over a flat plate. So what we're doing right now is just simply making the geometry for said flat plate. Okay, so we're going to go here. I'm going to go and make our grid settings, and I basically just turned show in 2D on, snap 0.1 and 10. Alright, so now we're actually going to put in our geometry, and as you can see, here's the grid now. And we're going to do a rectangle. Start from the midpoint, and you can make it whatever you want because we have to put the constraints on. So, or not the dimensions. We have to put the dimensions on. Now, in the project, it gives us that it's 100 centimeters, but since we're working in meters, we're going to keep it in meters. So that's 1 meter. And then put a constraint here. And this is going to be 0.5. Because it needs to be tall enough for us to see anything that's going on, because our boundary layer is actually going to be really tiny. So we don't want to make it too tall where it's like you're not going to be able to see anything. But we want to make it like kind of exaggerated so that, you know, it's present. Alright, so there is that. Okay, so we got some of our stuff. And then click on our sketch. Do surface. Apply. And generate. Alright, so now we have our actual geometry shape in 2D. And this is really all that we're going to need from here. Oh, there it is. Let me just make sure. Yep, we're good, dimension-wise. Okay, so now, always update the geometry, just in case. Okay, and then we're going to go into our mesh. Alright, now we are back. Alright, so the first thing that we're going to do is actually mesh this bad boy. And it's going to look like that. And so what we really want to do, the point of this meshing step is that we want to create a really fine layer of mesh towards where our boundary layer is going to be present on the bottom of the, or actually the top of the flat plate. And we want it to be super constrained down there. So what we're going to do is create our sizing for the mesh and do number of divisions. So this is going to just divide our things into segments so that when we do the velocity profile, it can show us how the velocity profile changes. Okay, 2 edges, number of divisions. So then now we'll create another sizing. And it's going to be for right here, this inlet. And this is going to be for number of divisions. And this is going to be 60. Okay, so quick update. I had to change a little bit. So this one is going to have a bias factor, the big to little option of 70. And then this one is going to have a reverse bias to itself so that it's flipped like that, as you can see. Yep, now everything looks good. Okay, so now we're back. We're also gonna do a face mesh of the entire thing. It's in quadrilaterals, so we're good. All right, so now we can go ahead and generate this mesh. And this is how you can tell when it's working. Perfect. Okay, so this is what we're going for. We want these grid lines to get super, super fine here, down at the bottom, because that's really the part that we're analyzing, is that boundary layer. So when the mesh is more refined, it's going to give us more accurate results, which just makes everything easier. Okay, so the next part is going to be pretty simple. It's just going to be naming. So we're going to call this is our outlet, and this is our inlet. This is what we would call our far field pressure. Just going to do P. And then this is the actual flat plate. I'm just going to call this the flat plate. Okay, let's make sure we got all of our decisions. Oh, and of course, we can't forget, this is our actual test section, like our airflow. Okay, so now that we've got everything meshed, this, where you come and you update, okay? You have to update, or else the platform is going to have absolutely no idea what to do, or that you even updated your geometry. Okay, so now we're going to go into setup, and we're going to do double precision. Okay. All right, we're making it through, guys. Okay, so now we finally have our actual model here. So first things first, we are obviously doing this in a laminar airflow. Makes things simple. So we got laminar flow, materials. We're using a fluid that is air. Okay, so we're given that our density is 1.2 and that our viscosity is 1.8. Let me just double check. That's what he said. It looks like it's literally the same thing, just less precise. So let's change that. Create it. Our boundary conditions. So we were told that the free stream velocity is 2 meters per second. So definitely want to apply that, or else we're not really going to get very much results. Outlet. This is just me prevent reverse flow, because we don't want the flow to reverse on itself. So that's just something you want to put in there. Apply, close. That reminds me to double check. Okay, we're good. Double check. Okay, we're good. Okay, so what I wanted to show you guys is that this far field pressure right here, this section, we do want to change its type to symmetry. Took me a little second to remember exactly how to do that. Okay, so now we should be all good to go. Everything is checked boundary conditions wise. All right, now one other thing that we're going to want to do, change the residuals. So do, right now it's to the -3. I want to do to the -6. So 1, 2, 3. It's probably easier to do just E, but 3. It's kind of more fun to do this. 2, 3. Okay, so now that we've got all of our things set up, we can go into initialization and initialize in the hybrid. Oh wait a second. Let's do 1,000 iterations. And here, there is my initialization. Let me go to not that. Let me go to run calculations. This one we'll do. You know what? We'll do 5,000 because I want it to be really, really particular. Yay! That's what we like to see. Now we are going to get into the contours and such that we want to see. Okay, so in the project outline, part A says, get velocity with vectors contours and pressure contours around the flat plate. Okay, so let's do that. So velocity with, okay, let's do that. Velocity with vectors contours. Okay, so yep, this is what we want to see. So this is like, this is a direct visualization of the boundary layer. So down here at the end, it's like super defined. You can see how tiny of a value it gets at that end. And then what we should see is that at the beginning, look at that, the boundary layer is only just starting to form. And as you progress, you just keep getting more and more and more and more. Okay, so that's what I believe it is. So now we're going to make our contours. So I'm going to do total static and dynamic pressure. I'm just going to hit all 3. Right, so this is what static pressure looks like. It's obviously much, much larger here. Okay, gonna get a new one. Make it dynamic. Alright, so this one is actually really cool because you can literally see the boundary layer and how small it is. And you can actually see the growth of the boundary layer. Super cool. As you start at the beginning, it's like almost non-existent. Like, look at that. So look at the difference between that. Okay. And then finally, we're at the, so that took a little bit more time than I thought it would. But, yeah. So there's our contour of dynamic pressure. And then let's do total pressure. And of course, it's going to look almost identical to dynamic pressure. And then we're going to do our velocity, yep, velocity magnitude, save and display, close, and this is what it's going to look like. So that should be part A. Now the next part to create velocity profiles, I think is easier to do in the results section. For this part, I'm just going to show you how to do everything that I did. So in the project outline, it says to have we're supposed to be doing the velocity profiles at 25 centimeters, 50 centimeters, 75 centimeters. So what you're seeing here is the inclusion of lines at those different locations. So basically all you do for that is you go to line, you make your line name, and then I'm just going to do one for example, the 0.25. You do 0.25, 0.25, and then for height, you're going to do 0.1, and you're going to do 200 samples. And so when you do that, it's going to give you a line at 25 centimeters, just like this. And then the height, the y coordinate that we put in there is so that when we plot it, which you'll see eventually, is more dramatic of a plot, as in like you can see it better, closer up, because that boundary layer is so tiny, so you don't want to do it too big. Okay, so let's just go back to this. So yeah, so as you can see, it's my 50, my 75, my 25. Okay, so oh, what's also in here that you can also do in here instead of doing it on the other one is your pressure and velocity contours. Doing that, here, let me show you. So all you would have to do to create it is go and click this, and you can create your contour, and then you go and label it with whatever you want to be labels you want to have symmetry 1 on. And for this one, we're using velocity U because that's what I want to have the contour. And then in the pressure one, you'll see that it's pressure as our variable because I wanted to see the static pressure. Okay, so those are just some neat things that you can do on here. So back to our lines. So to get those velocity profiles that I was telling you about, this is like the goal. This is what you want to get at the end. I have them labeled so you can visually see this is like our boundary layer thickness, and you can visually see that as the distance goes on, so from 25 to 75, the boundary layer gets thicker, which logically makes sense because it's thinner in the beginning and gradually builds up to be thicker as the plate goes on, more defined. We also saw that in the vectors. So this is just kind of visual of how that happened. So there's a trick to how to get these all here combined. So you're going to go here to this icon to chart, and it's going to bring you to this. You are going to name whatever you want it to be named. This is just what I did. You do XY line. So then this is where you are going to use your little lines here. So this is where that comes into effect. And you're going to add the different data series with this. So I was a little confused with that when I first did it, but I eventually figured it out, trial and error. So yeah, you want to add each of them, and then I named them for the legend's sake so you can actually read the graph. Very important. You don't want people not to be able to read it. And then obviously here you can see these are the names of my lines. So that's what I actually named them. This is the actual name of the line. So this is going to be what you want to use. Here, this is also important. Your x-axis is going to be your u velocity, obviously, because that's the direction the velocity is going in, is in u. And then your y-axis is just going to be y, the height, meters. Let's see, is there anything else? Nope. And then from here, to get it into Excel, you go to export, you pick you know, wherever you want it to go. I do all files, makes it easier for me. You pick wherever you want it to go, and it should convert into an Excel file automatically. At least mine did, which was very convenient. Very nice. This is also our boundary layer thickness, is these heights that it reaches right before it splits off. So next thing that we're going to do is go to our plots, and we are going to go to wall fluxes, and this is going to be wall shear stress. Okay, there we go. Sometimes it's a little bit ridiculous. Yes, I'm going to do skin friction coefficient. This is skin friction coefficient. All right. And then, oh, I should also explain that. To save these plots, you do a write to file, and then you save it. So I've already done that. So yeah, you just write to file and then save it in whatever folder you want to keep it in. Part D, get the drag coefficient for the flat plate using Fluent. Okay, so this part is going to be a little different. So what we're going to do for this one, to get our drag coefficient, we're going to go to report definitions, new, force report, drag. We want it to be our drag coefficient on our flat plate. I'm going to hit compute. Okay, and here is our drag coefficient right here. So yep, that should be everything, guys. Hopefully that was helpful. Hopefully I shared everything I needed to. And yeah, it's a very interesting project. You really get to see boundary layer at work. So it was cool to see that visually. But yeah, that should be everything. And that will be all, folks. Okay, bye.